We're going to learn exactly how to diagnose a faulty fuel tank pressure sensor, the FTP sensor, like a true professional. That means we're focusing on electrical testing, logical workflows, and hard data. By the time we're done here, you'll know how to pinpoint the real issue without just blindly firing the parts cannon at the car. To set the stage, I want you to picture this real-world case study. A customer's car rolls right into our bay. The check engine light is glaring at you. You hook up your scanner and immediately see that the EVAP readiness monitors are showing as incomplete. Worse, as you walk around the back of the vehicle, you're hit with a very strong, distinct smell of raw gasoline. The customer is super frustrated because they just failed their state emissions inspection, and they want answers right now. So, apprentice, how are we going to fix this?
Okay, let's dive into this. Here is our logic-based diagnostic game plan for today. 1. The component. 2. Symptoms and codes. 3. Electrical workflow. 4. Replacement rules. And 5. Apprentice quiz.
Section 1. The component. Before we even think about pulling codes or tearing things apart, we've got to understand the hardware. Meet the fuel tank pressure sensor. This little piece of tech is usually mounted right on top of the fuel tank, or sometimes integrated into the fuel pump module. Mechanically speaking, it's a piezoresistive transducer. Now, in plain English, that just means it constantly monitors the EVAP system's health by measuring both positive pressure and negative vacuum inside that sealed fuel tank. As the pressure changes, the internal resistance of the sensor changes. It literally takes that physical pressure change, converts it into an analog electrical voltage signal, usually sitting somewhere between 0.5 and 4.5 volts, and shoots that signal straight to the engine computer. What's really interesting here is this tiny number, 0.02 inches, or just half a millimeter. That represents the microscopic EVAP leak size that this sensor is responsible for detecting. The engine computer seals the system, watches the pressure data from this sensor, and if it sees a pressure drop indicating a hole the size of a tiny pinprick, it sets off the alarm. That is an incredibly tight tolerance. Section 2. Symptoms and codes. Let's talk about how the vehicle actually behaves when this highly sensitive sensor starts feeding the computer garbage data. When the sensor goes rogue, the drivability issues really begin. The customer might complain about sudden drops in fuel economy, a horribly rough idle, or hard starts right after refueling. Why? Well, because bad sensor data totally messes up the engine's purge valve timing. The computer thinks the tank is under immense pressure and inappropriately opens the purge valve, absolutely flooding the engine intake with excess fuel vapor. This creates a severe rich condition that causes the engine to just stumble and stall out at low RPMs. Now listen up, because I need to put on my serious mentor hat for a second. We never, ever ignore a strong gasoline smell. Raw fuel vapors escaping from a compromised EVAP system are a severe health hazard and a massive fire risk. Furthermore, if the sensor fails and causes the system to improperly manage the tank venting, extreme negative pressure can build up. I have literally seen extreme vacuum lock completely collapse and crush a plastic fuel tank inward. It's a serious safety issue. Let's grab the scanner. You'll often see EVAP codes like P0450, which points directly to a pressure sensor malfunction. But I need to warn you about a massive trap for rookies, the dreaded P0456 code, which stands for EVAP small leak detected. A P0456 can definitely indicate a real physical leak, like a cracked hose somewhere. But it can also be a completely false reading caused by a lying FTP sensor. You cannot just assume there's a leak without doing your testing. This brilliantly illustrates how we use our code knowledge to actually guide our electrical testing. Let's compare P0452 and P0453. A P0452 is a low input code. This usually means the sensor signal is stuck at 0 volts, which strongly indicates an electrical short to ground somewhere in the wiring harness. On the flip side, a P0453 is a high input code, meaning the signal is stuck at 5 volts, which points to an open circuit or a broken wire. These codes are telling you exactly what kind of electrical fault to go looking for. Section 3. The electrical testing workflow. All right, this is where the real shop floor action happens. As professionals, we always test the electrical circuits before we ever condemn a part. Here is your exact chronological diagnostic workflow. You do not just start ripping out seats or dropping the fuel tank. First, we check live scan tool data. It's the least intrusive step. Second, we get eyes on the sensor for a visual connector inspection to look for melted insulation or corrosion. Third, we pull out the digital multimeter to verify our power and ground. And fourth, we do a manual vacuum pump check. Here's your mental cheat sheet for step 3, the multimeter test. Before you condemn the sensor, you absolutely must verify the harness is delivering power. You need a solid 5.0-volt reference voltage coming from the computer. Your dedicated sensor ground must read less than 0.1 volts. And, crucially, if you take the gas cap off to put the tank at atmospheric pressure, the signal voltage on a completely healthy system should sit right in the middle, at around 2.5 volts. While you're monitoring this live data with your scanner, pay close attention to how the voltage behaves under engine load and during purge cycles. A healthy system is going to show a steady, predictable voltage curve as the pressure changes. But if you see wildly erratic fluctuations on the screen where the voltage is jumping up and down with no actual pressure change, you're likely looking at a sensor suffering from moisture intrusion right in the connector or heat exposure that's damaged the internal circuitry. So the absolute crucial point here is how we definitively prove whether the tank actually has a physical hole or if the sensor is just electrically blind. We take our manual handheld vacuum pump, attach it to the sensor, and apply a small, controlled amount of vacuum. While we pump, we watch the live voltage data on the scanner. If we apply vacuum and the voltage drops accordingly, the sensor works, meaning that P0456 code is a real mechanical leak. But if we apply vacuum and the voltage just flatlines, the sensor is dead.
Section 4. Replacement rules.
Let's say the voltage flatlined and the sensor is undeniably dead. When it comes to ordering parts, my advice is to always stick to precise OEM sensors. Remember that 0.020-inch tolerance? Modern emission systems are incredibly tight, and cheap aftermarket sensors frequently read slightly out of spec right out of the box, causing recurring diagnostic trouble codes. Also, be aware of what you're working on. Some cars have standalone sensors that are super easy to swap, while others use integrated fuel pump modules, which means you're going to be dropping the entire fuel tank to complete the repair. And when you actually go to install it, please don't make these common beginner mistakes. First, if the old connector has green corrosion in it, you must clean it or replace the pigtail. Plugging a brand new sensor into a corroded connector is going to destroy the new part almost instantly. Second, respect the torque specifications. Most of these sensors thread right into plastic vapor lines and only require about 10 to 15 newton meters of torque. If you over-tighten it like a gorilla, you'll literally crack the brand new sensor body before you even start the car.
Section 5. Apprentice quiz.
All right, put your tools down. Question number 1. What is the absolute most critical step you must perform before you tell the customer they need a brand new FTP sensor? Think back to our electrical workflow. Test, don't guess. You absolutely must verify the 5-volt reference and the ground circuits at the connector with a digital multimeter. Why? Because a bad ground or a missing 5-volt reference from the computer will mimic a completely dead sensor perfectly. If you skip this, you'll install a new sensor, and the car is still going to be broken. Question number 2. You've got a P0456 small leak detected code. How do we definitively prove if it's just a lying, faulty sensor or an actual physical mechanical leak in the fuel system? Let's see how this builds our confidence in the repair. You use your manual vacuum pump. By applying manual vacuum and physically verifying that the sensor's voltage sweep changes on your live scan tool data, you completely remove the guesswork. You prove the sensor's capability entirely independently of the sealed tank. And finally, our last question. I really want you to think about this one as you head back to the bay. After you install the new part, are you just erasing the trouble codes, handing the keys to the customer, and hoping the EVAP monitor's set? Or are you actually verifying the repair by taking the car through a complete, specific EVAP drive cycle? Remember, just erasing codes doesn't fix the car, and an incomplete readiness monitor is still an automatic emissions failure. Don't be a parts changer, be a diagnostician. Keep learning, keep testing, and I'll see you on the next one.